Have you ever wondered how big industries get something valuable, like oil, out of seeds without wasting anything? Well, it's all about washing, but there's a trick to it, a magic number of washing stages to do it just right. And today, we're going to figure out exactly how to calculate it.
Right? I mean, think about it. You're trying to get every last drop of oil from a ton of seeds, or maybe every speck of gold from a pile of ore. How do you wash away all the junk without losing the good stuff? It all comes down to maximum efficiency, and we're about to crack the code.
Okay, so let's take a look at the machine that does the magic. This is a countercurrent unit. Now, see how the solids, we call that the underflow, are moving one way, and the washing liquid, the overflow, is moving in the exact opposite direction? That setup is absolutely brilliant. It means the dirtiest material gets hit with the dirtiest water, and the almost clean stuff gets a final rinse with the brand new fresh liquid. It's a super efficient way to clean.
So here's our game plan for today. First, we'll dig into what makes this problem tricky in the first place. Then, we'll unpack the equations we need, and don't worry, we'll make it really simple. After that, we'll walk through the actual step-by-step method. And finally, we'll put it all to the test with a real-world example of recovering oil. So what's the big deal? What actually makes this calculation so complicated? Well, it turns out it's not always as simple as it looks, because one key factor keeps changing on us. And that tricky part is something called variable underflow. All that means is that as the solids get cleaner, the amount of liquid they're holding onto actually changes. You know, think of a sponge. After you wring it out a few times, it holds less and less water, right? It's the same idea. And because of that change, a simple one-size-fits-all formula just won't cut it. We need a method that can adapt at every single stage. To deal with that variable underflow, we're going to need the right tools for the job. So let's break down the key equations that are going to let us march through this process, one stage at a time. Okay, I know this looks a little scary, but don't panic. This is our main tool, the operating line equation. Really, all this thing does is help us figure out how much of the good stuff, our solute, is left after each wash. It's just a way to predict what's going to happen in the next step, based on what just happened in the last one. Now, to get that main equation to work, we need a couple of little helpers. You can think of them as the support crew. The first one tells us how much liquid is still clinging to our solids, and the second one helps us figure out how much of our valuable solute is left in that liquid. They work together to feed our main equation. So let's quickly meet the main players here. X is basically how concentrated our valuable stuff is in the liquid. W is how much of that liquid is stuck to the solids, and S is the one we really care about. It's the actual amount of the good stuff we're trying to get back. L and V are just for the washing liquid. That's really all you need to know for now.
Okay, we've got our tools. Now, let's lay out the exact plan of attack. This is the repeatable process we're going to use to find our answer.
And here's the beautiful thing about this method. It's a loop. It's just a cycle. We start with what we know before the first wash. We use our equations to calculate what things look like after that first wash. Then we stop and we check. Have we reached our goal? If the answer is no, we take those new results and we plug them right back into the beginning of the loop to simulate the second wash. We just keep doing that stage by stage until we hit our target. You know, it's worth mentioning that you can also solve this whole thing visually. If you plot the data on a graph, you can literally draw steps to see how each stage gets you closer to the goal. It's pretty cool. But for us today, we're going to stick with the step-by-step calculation. All right, enough theory. Let's get our hands dirty and see how this actually works in the real world. We're going to take everything we just learned and apply it to a practical oil recovery problem. So here's our mission. We've got this vegetable seed material, and it's full of oil. We need to wash it with a solvent to get 90% of that oil back. The big question is simple. How many of those washing stages do we actually need to build to hit that 90% recovery goal? Let's put some hard numbers on that. We start with 0.4 kilograms of oil per second mixed in with our solids. Now, if we want to recover 90% of it, that means we have to wash out everything except for 10%. So our target, our finish line, is to get that remaining oil down to just 0.04 kilograms. That's the number to beat. Okay, time to roll up our sleeves and fire up the calculator. Let's jump into the loop and figure out what happens after just one stage of washing. So we take our starting numbers and we plug them into our equations. After all the number crunching for this first stage is done, we find out we're left with 0.266 kilograms of oil. Now for that all-important check.
Our result is 0.266, which is still way higher than our target of 0.04. So what does that mean? One stage is definitely not enough. We've got to keep going.
And here's where the loop really kicks in. The output from stage 1 now becomes the input for stage 2. We just take our new values and run them through the exact same process all over again.
And after we run the numbers for stage 2, we get a new result. We're now down to 0.141 kilograms of oil. Hey, we're making progress. We're getting closer.
Time to check again. Is 0.141 less than our target of 0.04? Nope, still not there yet. So 2 stages aren't quite enough either. Let's go for a third.
Onward to stage 3. The results from stage 2 are now our starting point. You know, I've got a good feeling about this one. Let's see what happens.
Okay, after running those calculations for a third time, we get our new result, 0.01615 kilograms of oil remaining.
And there it is. That's our magic number. The answer is 3. So why 3? Well, because our result after that third stage, 0.01615, is finally less than our target of 0.04. We've officially crossed the finish line. We've hit our goal of recovering more than 90% of the oil. We did it! So, we just solved one very specific engineering problem. But this exact kind of precise step-by-step calculation is happening all around us, all the time. From how medicines are made to how our food is processed. It really makes you wonder, where else is this kind of invisible precision engineering quietly at work?